Okay, this video is intended for pre-calculus workload 910. It is the first half of the algebra review part one. So there'll be another video for the second half of algebra review part one. This is meant to accompany the homework assignment to kind of give you some instruction as to how it's supposed to be done. And let me fix my window here because I feel like I'm getting some weird static. Is that better? Maybe. Yeah. Cool. So we're going to go through this. Hopefully it is helpful. First, we're going to talk about exponents. So the point of an exponent is really just repeated. Oh, I'm James, by the way. Sorry, I'm James. Welcome, pre-calculus, workload 910, right? Workload 910. Yes, workload 910. So exponents are just repeated multiplication. What that means is when we write something like 6 squared, we mean 6 times 6. And then if it's small enough, we usually like to simplify it to its actual value. 6 times 6 is 36. Similarly, 2 to the fifth means 2 times 2 times 2 times 2 times 2. And that's probably small enough. 4 times 4 is 16. 16 times 2 is 32. Same deal here. 5 cubed means 5 times 5 times 5, which is 125. I will point out if we had a number that was like 5 to the 7th, we'd probably just leave that as 5 to the 7th because multiplying it out and getting whatever number that is kind of a pain. So that's repeated multiplication. That's what exponents represent. As long as they are positive integers. When they get to be fractions or negative numbers, there's a little bit more to it. So let's continue on. Multiplying expressions with the same base that also have exponents. So for example, if we have something like 2 to the third times 2 to the fourth, let me move this keyboard out of the way here 1 second. Sorry. Oops, I'm trying not to, this cord is a little finicky, so I don't want to mess with it here. Sorry. Terrible. Terrible first video. Okay. So, yeah. So, yeah, see, the cord's finicky. So multiplying expressions with the same base. Let's switch this down just a little bit here. 2 to the third times 2 to the fourth. All that means is, well, 2 to the third is 2 times 2 times 2. 2 to the fourth is 2 times 2 times 2 times 2. How many 2's are we multiplying together? 7 of them. So that's going to be 2 to the 7th power, which we could have gotten by just adding the exponents 3 and 4. So when we have a base to a power times the same base to a power, we can add those powers together and say we have 2 to the 3 plus 4, which is 2 to the 7th. So that's really how we're getting there, instead of writing it all out like this. And then you could simplify that 2 to the 7th is a little bit big. It is equal to 128, but I would probably leave it as just 2 to the 7th. Same deal, 10 squared times 10 to the third. We're going to add those powers because that's 2 tens multiplied together and 3 tens multiplied together. And 2 to the 10, 10 to the 2 plus 3 is just 10 to the fifth, which again, if you multiply that would be 100,000. You don't need the comma there. Some people like to write it because it helps them keep track of things. But again, we're really getting that because it's 10 times 10, that's 10 squared. 10 times 10 times 10, that's 10 cubed. And then that's 5 tens multiplied together, which is the same as 10 to the fifth. All right. Just like with multiplying expressions with the same base, we're also going to talk about dividing expressions with the same base. So if you have something like 3 to the 7th divided by 3 to the fifth, well, every time I have a base to a integer, a positive integer power, I'm going to go back to thinking of just repeated multiplication. 3 to the 7th really is 3 times 3 times 3 times 3 times 3 times 3 times 3 7 times. And 3 to the fifth is 3 times 3 times 3 times 3 times 3 5 times. This is division. So 3 divided by 3 is 1. 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 So what we really have here is 1 times 1 times 1 times 1 times 1 times 3 times 3. Multiplying by 1 doesn't change a value. So really we just have 3 squared, which is 9. But really the point here is that the 3 to the 7th divided by 3 to the 5th ends up equaling 3 to the 7 minus 5, which ends up being exactly 3 squared, which is 9. So when you divide expressions with the same base, we end up subtracting the powers or the exponents. Same deal here. 2 to the 10th divided by 2 to the 6th is going to be exactly 2 to the 10 minus 6, which is 2 to the 4th, which you could then simplify as 2 times 2 times 2 times 2, which is 4 times 4, which is 16, or however you want to get there. Again, I could write it out. I don't think I need to. I'd have 10 2's multiplied together on top, divided by 6 2's multiplied together on the bottom. 6 of them would essentially cancel, right? 2 divided by 2 is 1. It remains at 1. And then multiply by 1 doesn't change anything, so you're left with the 2 to the 4th. What about a power to a power or an exponent to an exponent? So if we have 2 to the 3rd to the 4th, well, let's write it out. That's 2 to the 3rd times 2 to the 3rd times 2 to the 3rd times 2 to the 3rd 4 times. But that's really 2 times 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 2. How many 2's are we multiplying together? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which we could have arrived at by doing 2 to the 3 times 4. So when you have a power to a power, you end up multiplying those exponents or those powers together. This one you could, so if you ever played that game, the 2048 game where you like slide the things around and things double, 2 to the 10th is 1024, 2 to the 11th is twice that, which is 2048, and 2 to the 12th is twice 2048, which is 4096. But really, you should just leave it like that. 5 squared cubed is 5 squared times 5 squared times 5 squared, which is really 6 5's multiplied together. So it's 5 to the 2 times 3, which is 5 to the 6th. And I would just leave it like that. I don't know what 5 to the 6th is. What about the 0th power? That one is always kind of tricky, and I feel like I didn't do a good job of leaving myself enough room here. So I'm going to steal a piece of paper over here to give myself a little bit more room. I will tell you 6 to the 0, or any positive number to the 0th power, is 1. But why? Well, it's because of how this additive law of exponents works. In fact, the first thing we did here, when we talked about, or not the first thing, the second thing we did, where we multiplied two things with the same base and added the exponents, well, that's kind of a general rule that's always true. Whenever you multiply two things together with the same base, you always add their exponents together. Well, that has to be true no matter what the exponents are. So for example, if you had, say, 6 to the 0 times 6 squared, and I probably don't need this piece of paper, actually, we'll see. That's going to equal, well, if I add those exponents, 6 to the 0 plus 2. And I just picked 6 squared because I know what 6 squared is. It's 36. But now look what happens here. I have 6 to the 0 times 36, right, 6 squared, equal to, well, 0 plus 2 is 2, and 6 squared is also 36. So look what happens here. I have something in this box multiplied by 36 equal to 36. The only number that could be is 1, because the only number that you can multiply by 36 and still get 36 is 1. So that means that 6 to the 0 has to equal 1. Alternatively, or kind of alternatively, here if I did the same thing, I could say 17 to the 0 times, let's pick an easier number, let's say 17 to the 1st is equal to 17 to the 0 plus 1. So I have 17 to the 0 times 17 to the 1st, or anything to the 1st is just whatever that thing is. So 17 to the 1st, 17 to the 1st is 17, and that's equal to 17. And instead of just saying that this thing in the box here has to be 1 because 1 times 17 is equal to 17, I could divide both sides by 17 and say, oh, look, 17 to the 0 times 17 divided by 17 is equal to 17 divided by 17. 17 divided by 17 is 1. So I end up with 17 to the 0 times 1 equal to 1. Well, 17 to the 0 times 1 equals 1, but anything times 1 is just itself. So this really just says So I'm running out of room here a little bit. 17 to the 0 is equal to 1. So any positive number raised to the 0th power is equal to 1. I will also point out this kind of interesting conundrum here, which I know things are a little tight here. Sorry for the squeezing stuff in. So -5 to the 0 is equal to +1. Because again, you have a base to a 0. So really, any positive or negative number raised to the 0th power is equal to 1. And again, you could do the same kind of thing. You could say something like -5 to the 0 times -5 squared is going to end up equaling -5 to the 0 plus 2, which is -5 squared. And the same argument persists. This thing here has to be equal to 1, so that 1 times this number is equal to the same number. On the other hand, -5 to the 0, we have to think about order of operations here. We have this thing where we have to do an exponent before a subtraction or a minus sign. So since there isn't a parentheses here, the exponent takes precedent, and this really becomes -5 to the 0. 5 to the 0 is 1, so we have -1. Just be careful. Sometimes that kind of comes up. It's a little tricky. All right, moving on. Negative powers / exponents. So what's 4 to the -1 equal to? Well, you probably know, but here's how we justify it. I'm going to do the same kind of thing I did before. I know that 4 to the -1 times 4 to the +1. Well, if I have to add those exponents, I get 4 to the -1 plus 1. So I have 4 to the -1 times 4 to the 1 equal to 4 to the 0. But 4 to the 0 or anything to the 0 except for 0 to the 0, that's a whole nother thing we learned about in calculus. But 4 to the 0 is equal to 1. So then if I divide both sides by 4 to the 1, I can say that, in fact, let's just write it out. I can show my work. 4 to the -1 times 4 is equal to 1, dividing both sides by 4. So let's say divide by both sides by 4 to the 1, even though you don't really need the exponent of 1 there. I'm going to write it in anyway. So 4 to the 1 divided by 4 to the 1 is 4. Sorry, 4 to the 1 divided by 4 to the 1 is 1. So we have 4 to the -1 times 1, which is just 4 to the -1, equal to 1 over 4 to the 1. Or in other words, 4 to the -1 equals 1/4. So when you have something to a negative power, you can rewrite it as that same base to the positive power, but in the denominator if it was in the numerator. So essentially you switch places, you go to the place. So if it was in the denominator, it would end up in the numerator. Same deal here. This 7 to the -2 is going to end up being the same as 1 over 7 squared, which is 1 over 49. But the reason that works is because 7 to the -2 times 7 to the +2 is equal to 7 to the -2 plus 2 is 0. So we're really saying 7 to the -2 times 7 squared is equal to 1. We can divide both sides by 7 squared and say that 7 to the -2 is equal to 1 divided by 7 to the 2nd. And then we can simplify 7 squared as 49. So that's equal to 1 over 49. So that's why that works the way it does. And just to kind of tack on one more example here, if you happen to have something like 1 over 8 to the -2nd, it would be appropriate to write that as 8 to the +2nd. You switch where it is in the fraction. If you go from the denominator to the numerator or from the numerator to the denominator, you switch the sign of the exponent. And then you could say that's 64. Fractional exponents are also the same as radicals. They're just a different notation. But again, why do they work the way they work? Well, you might know that 9 to the 1/2 is the same as the square root of 9, which you probably know is 3. But why is it 3? Well, let me scooch this down a little bit, trying to keep the pertinent stuff on the page here. This works because 9 to the 1/2 times 9 to the 1/2 is equal to, well, if we add those powers together, 1/2 plus 1/2 is 2/2, which is 1. And 9 to the 1 is just 9. So look what we have here. We have a thing, 9 to the 1/2, multiplied by the same thing equal to 9. So we have 9 to the 1/2 times 9 to the 1/2 equal to 9. And the only positive number, and it does have to be positive for reasons we'll get into in a second here, the only positive number that this works for is positive 3. 3 times 3 is 9. There isn't any other positive number that works. So that means that 9 to the 1/2 must be 3 because 3 times 3 is 9. The reason it's not -3 and it's not a plus or minus 3 is because we define the square root or the 1/2 power or any even root like a 4th root or a 6th root to be the positive root. And again, it's really because we want the whole thing to be a function, but that's a topic for another day. For 8 to the 1/3, same kind of deal works. That's also equal to the cube root of 8. So when you say the square root of 9, you're really looking for the number that when you multiply it by itself 2 times, so something times something, it equals 9. The number is 3. Same deal for 8 to the 1/3, except now you're looking for a number that when you multiply it by itself 3 times, so something times something times something is equal to 8. And that's again because we want 8 to the 1/3 times 8 to the 1/3 times 8 to the 1/3. 1/3 plus 1/3 plus 1/3 is 3/3, which is 1. So you're looking for a number multiplied by itself 1, 2, 3 times to equal 8. And that number is 2. So 8 to the 1/3 is equal to 2 because 2 times 2 times 2 equals 8. You don't have to show this work when you do these kind of problems, but that's the way you can justify that it actually does what it does. So when you're looking at fractional powers, which are the same as roots, you're just looking for a number that you multiply it by itself that many times to get the inside of the root. So for example, the square root of 25 is 5 because 5 times 5 is 2. The cube root of 64 is 4 because 4 times 4 times 4 is 64. And so on and so on. And then when you have fractional powers that are not just a 1 over something that you write, we couldn't just write this as the 4th root of something. You could write it as either the 4th root of 16 cubed. 16 cubed seems terrible. You could also write it as the 4th root of 16 cubed. Or if you're me, I would probably prefer to write it as 16 to the 1/4 cubed. If I'm trying to simplify a fractional power where the numerator and the denominator are both not equal to 1, I would always choose to do the denominator part first and the numerator part second, because 16 to the 1/4 is 2, right? 2 times 2 times 2 times 2, 4 times is equal to 16. And then 2 to the 3rd is 2 times 2 times 2, which is 8. That's how I would approach fractional powers where the numerator and the denominator are not equal to 1. I think there's something else to say here. No, that seems all right. I guess I could throw another example at you. Yeah, sure. Just to fit one more in here, an extra one. If you had something like, say, sure, 27 to the negative 2/3, I would write that as 27 to the 1/3 to the negative 2. The cube root of 27, or 27 to the 1/3 power, you're looking for a number that you multiply it by itself 3 times to get 27. The number is 3 because 3 times 3 times 3 is 27. So it's 3 to the negative 2, which is then 1 over 3 squared, which is 1/9. Okay, last page here. Simplifying expressions with variables and exponents. So sometimes you have gnarly looking things like this, and you want to simplify it in a way so that all of your variables have positive powers. So the first thing I would do is take each of these expressions that have powers on the outside and kind of square them each. So I could write this as x cubed squared. I'm probably writing an extra step here. That's okay. Y to the 4th squared times x to the fifth to the negative third times y squared to the negative third all over x to the sixth to the fourth times y to the seventh to the fourth. I probably would skip that step in general though, and just do the multiplication. X to the third squared is x to the sixth. Y to the fourth to the second is y to the 4 times 2, which is 8. X to the fifth to the negative third is x to the negative 15th. Y to the second to the negative third is y to the negative sixth. And then x to the sixth to the fourth is x to the 24th. Y to the seventh to the fourth is y to the 28th. And then I would probably combine terms on the top and the bottom if I can. So on the top, I have two different x's and two different y's. So I can multiply x to the 6th by x to the negative 15th. I'm going to add those powers. I'm going to get x to the 6 plus negative 15, which is the same as 6 minus 15, which is negative 9. 8, and then y to the 8 plus negative 6, and 8 plus negative 6 is the same as 8 minus 6, which is 2, divided by x to the 24, y to the 28th. I would probably subtract powers first, and say I'm going to have x to the negative 9 minus 24, and then y to the second minus 28. That's going to be, let's see, negative 9 minus 24 is negative 33. And 2 minus 28 is negative 26. I said I wanted both the powers to be positive, or all the powers to be positive. So I'm going to write those both in the denominator. I'm going to have x to the positive 33, y to the positive 26. And I can't have a blank on top. I've essentially divided both I've essentially divided by both those things. So the top has a 1 left over because when you divide by the same thing, something divided by itself leaves a 1. Cool. Let's do the same sort of thing here. I'm going to actually not write out the whole entire first step this time. Let's go ahead and do the following. I am going to write 9 to the negative 1/2. But x to the 8th to the negative 1/2, I'm going to do 8 times negative 1/2 is negative 4 and get x to the negative 4. Same deal. I'm going to get 18 times negative 1/2 is negative 9. So I have y to the negative 9. Whoops, that looks a little ugly there. Sorry about that. 16 to the 1/4. I guess I could write some time symbols here. You don't really need them, but it's good to write them. X to the negative 4th to the 1/4. Negative 4th times 1/4 is negative 1. So I get x to the negative 1. And then y to the negative 12th to the 1/4 is going to be negative 12 times 1/4 is negative 3, or essentially 12 divided by 4 is 3. Same thing as 12 times 1/4. In the denominator, I have 8 to the negative 2/3. X to the 9th to the negative 2/3. 9 times negative 2/3 is going to be 9 divided by 3 is 3. 3 times negative 2 is negative 6. And then y to the negative third to the negative 2/3. Negative 3 times negative 2/3 is positive 6/3, which is positive 2. That's a y squared. Let's simplify a bit. I would probably change the signs of the powers on the numerical values. Specifically, the 9 to the negative 1/2 and the 8 to the negative 2/3, I would probably switch where they are in the fraction. So I'm going to rewrite this with the numbers out in front. So I'm going to write this as, I think I can fit it here. I'm going to leave the 16 to the 1/4 on top. And then the x to the negative 4th times the x to the negative 1, I'm going to add those powers. Negative 4 plus negative 1 is negative 5. So you get x to the negative 5. Same deal with the y's. Y to the negative 9th times y to the negative 3rd is negative 9 plus negative 3 is negative 12. So I get y to the negative 12. In the denominator, I'm going to bring down the 9 to the, oops, I forgot to bring up the 8 to the negative 2/3, sorry. And it's just, for me, it's easier for numbers specifically to deal with them as positive powers. So I guess I'll put the 8 to the positive 2/3 at the end over here. Even though that's kind of ugly. Oh well, such is life. In the bottom, I'm going to have a 9 to the positive 1/2. And I still have my x to the negative 6th and my y to the 2nd. Okay, couple things in this next step here. 16 to the 1/4 is 2, because 2 times 2 times 2 times 2 4 times is 16. And then instead of subtracting these powers, I'm going to bring the x to the negative 6 up as an x to the positive 6. So I have x to the negative 5th times x to the positive 6, so that when I put those together, I know the power will come out to be positive. In a similar way, I'm going to bring this y to the negative 12 down to the bottom as y to the positive 12, so that those powers end up being positive. Essentially, I'm looking at it and kind of seeing, like, I know if I bring it one place versus the other, the overall power will end up being positive. And then I'm still going to have my 8 to the 2/3. That is 8 to the 1/3 squared. In the denominator, I didn't write my y up top, right? I'm going to write in the bottom. I'm going to have my 9 to the 1/2, which is 3, right? It's the square root of 9. The x to the -6 is already taken care of, but I'm going to have a y squared times y to the 12th. Check, check, check. And then finally, 8 to the 1/3 is 2. 2 squared is 4. 4 times 2 is 8. Kind of funny, right? Just to point out, right? That part there is equal to 2. 2 squared is equal to 4. And then the 4 times 2, yeah, it's 8. X to the -6 times x to the 6. I'm going to add those powers. -5 plus 6 is 1. I got x to the 1, but I'm not going to write the 1 as a power because we typically don't. On the bottom, I have a 3, and I have y squared times y to the 12th, which is y to the 14th power. So 8/3, or I should say 8x over 3y to the 14th. It would also be acceptable to write this as 8/3 times x over y to the 14th. But if we're trying to write all the powers as positive and we have stuff in the denominator, we usually would probably leave it like this. Although either way would be acceptable. All right, that is the first half of the video for the first homework assignment. So second half will get posted soon-ish, and I'm looking forward to meeting all of you. All right, that's it.